So now we're going to learn about vectors, in particular force vectors, and what operations are valid with them and how we add them, subtract them, and so on and so forth. Once we're done, you should be able to resolve a two-dimensional vector into components along two directions, and you should be able to add vectors using Cartesian vector notations. We won't go through all of these activities, for example, checking homework and the reading quiz and so forth, but the bulk of these items we will accomplish in today's lecture. We'll skip the reading quiz. As I said, I have posted readings. I know most students don't usually do it. One thing that you might do is challenge yourself after this lecture by going back to this slide and decide what you think about which are the correct answers. So let's talk about why we would want vector addition, why that ability is important. So here's an example where we have three chains that are connected to an intermediate ring and then connected to a hook. Let's say that the hook is the concern. That's what we think might break. We need to somehow figure out how much total force is applied to the hook by F1 plus F2 plus F3. You see that the resultant vector Fr is what we're interested in, and the person who made this picture has started adding F1 and F2 together graphically. We'll understand in a moment how to actually add vectors, and it actually has a lot to do with Pythagorean's theorem or parallelograms. Pythagorean's theorem, if we're dealing with vectors in a space that is right angled to one another, or a parallelogram if we don't want to bother with the coordinate system itself, or if the coordinate system is not an orthogonal coordinate system. Now, there is a difference between scalars and vectors. For example, a scalar are things like mass and volume. These are things that have a magnitude but no particular direction. Whereas vectors are things that have both magnitude and direction. So things like force and velocity. If I tell you to go get in your car and go 55 miles an hour, you'll say, okay, but which direction, right? You can't just move at 55 miles an hour without, I mean, you could, but you'll be moving in some direction. You can't have one without the other, in other words. So a characteristic of a scalar is that it has some magnitude, could be positive or negative, whereas vectors have both magnitude and direction. For adding scalars together, well, you've been doing that since probably kindergarten or before, right? All you do is use simple arithmetic. You simply add them as you would any other way. But to add vectors, we have to use the parallelogram law, or we have to add components of vectors. And so the key thing here is that on a regular number line, you just have a single line. Whereas with vectors, we've got multiple directions and we have to add them together. So think about it this way. If you want to determine your total displacement when you get a compass, and let's say you go 50 paces north and then 50 paces east, how would you figure out how far in total you have moved from the initial position to the final? Well, you'd have to use Pythagorean's theorem, right? Square root of the sum of the squares, and figure out how much distance you've moved. That's really why vectors have to be added differently than scalars, whereas with scalars, the numbers are all just laid out along a linear line, so you simply add them. They're already all in the same direction, in other words. Now, in order to indicate which are scalar and which are vector quantities, with scalars, we won't use anything special, but with vectors, I'll often write a line above it. I can't write it in bold font, but obviously textbooks and slides and things like that can be in bold font. Or we could also use an arrow or a caret above it. If you look on your keyboard, if you're watching this on a computer, look at the number 6. There's a caret character above the 6. And that above a number or a variable would indicate that that thing is a vector that has both magnitude and direction and is not just a simple scalar. So in the PowerPoints that we're going through, the vectors will be indicated in red and in bold and italics to make it easy for us. Well, I say that, and then the slides show us a vector that is in bold but not in red or italics. We'll have to understand it by the context. Anyway, so you notice that the vector A is indicated as an arrow there on the left. Well, how do we multiply scalars by vectors? Well, it's easy. All that the scalar really does is scale the length of the vector. It doesn't change its direction, because think about it. Scalars don't have direction, only vectors do. So if you multiply vector A by 2, you will simply get a vector that is twice as long. If you multiply the vector A by -1, all you've done then is reversed the direction of the vector. Whereas if you multiply it by, say, -1/2, you reverse the direction and you've made it shorter. In fact, half as short. Now, division with a scalar is essentially multiplication by a number potentially less than 1, right? So division and multiplication are essentially the same thing. So how do we add two vectors together, for example? Oh, by the way, could you add a vector and a scalar? No, because the scalar doesn't have any direction, so that doesn't make any sense. But we could add two vectors together. Remember the chain we saw a moment ago, and we had 3 force vectors. What we'd like to do is add those together. How do you do it? Well, let's take a simpler case of just 2 vectors, vectors A and B. If you put those 2 vectors tail to tail, then what you need to do is draw 2 lines. One line that is at the tip of A and parallel to B, and another line that is at the tip of B and parallel to A. Now, you might realize drawing lines is something you can do in any CAD package, so you can actually add vectors graphically in CAD if you like. So once you've drawn these 2 lines where they intersect at point P, simply draw a line from the tails of A and B all the way to point P, and that is the sum of vectors A and B. That's called the parallelogram law. However, there's another way to do it, and that is to simply take the 2 vectors and move them around so that they are tip to tail. So in other words, for example, put the tail of B on the tip of A, and then go from the tail of A to the tip of B, and that is the resultant vector. That's the sum of the 2. It's the same thing that I mentioned earlier. Imagine walking 50 paces north and then 50 paces east. The resultant displacement is, well, I should have made the numbers easier. Let's do that. Let's say we walk 30 paces north and 40 paces east. Well, then the total displacement is 30 squared plus 40 squared and then square root. And so that is simply 50 paces. Now, in this case, notice that A and B are not perpendicular to one another, so it couldn't exactly use Pythagorean's theorem. This is a more general triangle, but graphically, we could simply add A and B, or you'll see later we can add the components. How would you subtract a vector? If we can add, we should also be able to subtract. So how would you subtract? Well, it's easy. You take one of the vectors and turn it around. Whichever vector you want to subtract, that's the vector you turn around its direction. In other words, you multiply it by -1 and then add it to the first vector. And then that's the equivalent to subtracting the vector. How could you add more than 2 vectors all at the same time? Well, the easy way to do it is to use the tip-to-tail method. Simply take however many force vectors you have and place them all tip-to-tail in a chain, and then go from the tail of the very first vector all the way to the tip of the final vector, and that would be the sum of those vectors. What about if we want to break a vector up into parts? Instead of adding vectors together, could we break them up into components that are in particular, maybe convenient directions? Well, yes, we can. That's called resolution of a vector. It's just breaking it into components. So you notice that in figure A, we have a force F, and we'd like to know how much force that imparts to the 2 cables that are both connected with eyelets there. So we've got direction V, which is along the lower cable, and direction U, which is along the horizontal cable. We'd like to know how much of force F goes into the horizontal cable and how much goes into the one that has some vertical component. So all we simply have to do is sort of use the parallelogram law in reverse. Simply draw the lines, as we said before, right, so that you've got a parallelogram, and then the sides of the parallelogram represent the magnitude of the 2 vectors. So, for example, F sub u is the amount of force, it's the contribution to the force in the horizontal cable that F gives, and F sub v is the amount of F that goes into the cable that has some vertical component. And we can prove this by simply taking F sub u and adding F sub v, and we get back the original vector F that we had. All right, so what if we have a vector and we'd like to resolve it onto coordinate axes? Most of the time we're dealing with a right-handed or a orthogonal coordinate system. All that means is that the angle between the axes is 90 degrees. You've dealt with XY planes for quite a while now, I imagine. And so what if we've got a vector in 2D space and we want to resolve it onto the X and Y axis, or see how far that F moves along the horizontal axis and how far it moves along the vertical. Well, it's pretty simple. In fact, our parallelogram would simply be a rectangle, right? And so all we'd have to do is place the base of vector F at the origin of the coordinate system, and then simply measure how far up the coordinate system on Y F F's tip is located, and that would give us the length F sub y, the amount of force in the y direction. And then from the tip of F down to the horizontal axis, the x-axis, would give us F sub x. So we basically are resolving them. Now, you might realize, since this is a right-handed coordinate system, what we're really doing is playing with a triangle. Imagine moving F sub y over so that it is at the tip of F sub x. So F sub x going over on the x-axis plus F sub y equals the resultant vector F. And you notice that what we've just done there is made a right triangle. And so you can use sines and cosines and tangents and all of the things that you would with a regular triangle or a right triangle in order to resolve F into x or horizontal and vertical components. So each component of the vector has a magnitude and a direction. So it's not like you take a vector and you resolve it into scalars. That's not what happens. What you get as a result are vectors, no matter how you dice it or you cut it up. Now, it's really important to understand the concept of the unit vectors. Since vectors are magnitude and direction, sometimes what we really care about is just the direction. And so, as confusing as it is, we introduce two different designations. The unit vector I that has magnitude of 1, or unity, so it's basically, it's not like it has no length, but it has unit length, and it is pointed along the positive x-axis. And then vector j, the unit vector, is pointed along the y-axis and also has a magnitude of 1. And the reason for doing this is so that we can express the components of the force or the vector or whatever we're dealing with in terms of a magnitude, which would be a scalar, and a direction. So we'll basically multiply the scalar by the unit vector. So for example, fx times I, where I is the unit vector, and f sub y by j, where j is the unit vector. So then f sub x and f sub y could simply be scalars that we multiply by their direction. So we're basically squishing them together by multiplication. But notice we haven't changed the size of f sub x because I has magnitude 1 and so does j. So here's an example where we have the vector from before on the left-hand side, and we can write that vector f as its magnitude, its length in the x direction, times the unit vector I, plus its magnitude along the vertical direction times the unit vector j. Now understand, there's an addition sign here. That doesn't mean that if you have the magnitude of fx, let's pretend it's 3, and the magnitude of fy, that you can just smash those together and say, well, then f is 8. That's not true, right? Because let's back up. If f of x is 3, well, let's see what would match. Let's make fx 4 and fy 3. Then you should know that the length of f, the magnitude of that vector, is 5 because it's a 3, 4, 5 triangle, right? But you couldn't take fx being 4 and fy being 3 and just add them together and say, well, the length of f is 7. That's not correct. Okay, if fx and fy were in the same direction, then you could add them, but they're not. So we're never going to take these two components of the vector and just mash them together into one thing. That wouldn't work. Now, we don't have to write f in this manner. Sometimes we will have a force that has negative components, and if that's the case, all we have to do is attach a negative sign on the front of the magnitude. And in the case on the right-hand side, you notice we have f prime that's being broken down into horizontal x and vertical y components, but it has a negative y component. So there we just attach a negative sign. Now, a lot of times what we'll do is we won't even write the positive sign. We'll simply write something like negative f prime sub y in the j direction. And all that indicates is that the component of the force f prime is in the negative j direction, whereas the component along the x-axis is in the positive x direction or positive I direction. Now, the x and y axes are always perpendicular at 90 degrees to one another when we use a coordinate system like this, and so we can set them or turn them to any orientation that we like, and all of this will still work. So adding several vectors, how would we do it? Well, the easiest way to do it is to take each of the vectors and resolve them into their components. So you see we have three vectors, f1, f2, f3. f1's in the first quadrant, f2 is in the second quadrant, f3 is actually in the fourth quadrant. And we take f1 and resolve it into its horizontal and vertical components. Take f2, do the same thing. Notice that f1 has all positive components in the I and j, or the x and y axes, the I and j directions, whereas f2 has all Well, no, that's not right. It has a positive magnitude in the vertical direction, but it has a negative magnitude in the x or the I direction is what I should say. F3, on the other hand, has a positive horizontal component and a negative vertical component. So the next step is to take all of the horizontal pieces of the vectors and just add those together because they all point in the same direction, and then add all the vertical components together and keep those two as separate things, a horizontal piece and a vertical piece. Now you might look at this and say, well, wait a second, you just said that all these vectors have the same horizontal direction, but I see that F1 and F3 in the x direction are in the positive x, but F2x is in the negative. That's fine. All that means is that we will subtract F2x from F1x and F3x. It'll all be clear here in just a moment. After that, after we've got the sum of all these things, then all we do is find the magnitude of the resultant and the angle where that resulting vector would be. Now, another way to do this graphically is just to rearrange all these vectors and move them around. For example, leave F1 where it is, take F2, put the tail of F2 on the tip of F1, and then take F3 and put the tail of F3 on the tip of F2. The resultant vector would be from the tail of F1 to the tip of F3. And so graphically we could do the same thing. We'll do it mathematically here instead, and I'll leave you to try that in SolidWorks or whatever package you'd like. So the resultant of the sum of the three vectors, F1, F2, and F3, would simply be F1xi plus F1yj, that's the representation for F1, okay, minus F2xi, because remember F2 has a negative component in the horizontal direction, plus F2yj, so that's all of F2, and then plus F3i, because F3 has a component to the right in the positive x direction. I think my camera's backwards, so I'm pointing in the wrong direction if you're watching me. And then negative F3y in the j direction because F3 has a negative component along the y-axis. Then just collect together all of the horizontal components, all the I pieces, and just add them with the sign that they've got. So you notice we have F1x minus F2x because it was in the negative direction plus F3x. Whatever that sum happens to be, that's the resultant in the x direction, which would be Fr sub x. Obviously, we don't have numbers in this example, but in a problem you would. And then we'd have F1y plus F2y, because both F1 and F2 have positive components along the vertical axis, minus F3y, because of course F3 has a negative vertical component. And whatever that resultant would be is Fry. Now, we haven't figured out the magnitude of the resulting vector, but we have written the vector, you notice, in Cartesian coordinates. We've got Frx, how long the vector is in the horizontal component, and notice Frx could come out positive or negative. It just depends on how big F2 is in this case. And Fry, which could also end up being positive or negative. But all that does is indicate to you the direction of the resultant vector along that particular axis. So then we would take that resultant vector, let's just pretend it turned out this way, it would be somewhat like this. And we've got Frx and Fry. What we'd like to know is the angle that that vector makes with respect to the x-axis. So we would simply pretend that this is a triangle, move Fry over so that it is at the tip of Frx, and then its tip, Fry's tip, would be on the same point as Fr's tip. And we could simply find the angle theta by taking the inverse tangent of Fry over Frx, just like you'd find the angle of a triangle by taking the inverse tangent of the vertical height of the triangle over the base length of the triangle, assuming it's a right triangle, of course. And then the magnitude of Fr, the resultant, is simply the square root of the sum of the squares. It's just Pythagorean's theorem to find the magnitude of the hypotenuse, the resultant of these two horizontal and vertical components. Now here's an example to work through. We've got three separate forces, and we'd like to find the magnitude and angle of the resultant force. You notice that they've been given to us a couple of different ways. For example, F1 is just vertical. It has no horizontal component. So how will we deal with that? Well, you'll see in a minute. You see that F3 has been given as it lies along a 3, 4, 5 triangle. Now, there's a really important point to note here, and that is that we're using geometry. We're using the angle of that arrow to break up the force into components. And you'll see how in some of the example problems I'll work for you later, how we're making a force triangle, or really resolving F3 into a triangle that is similar to this geometry triangle. Notice that F2, however, on the left-hand side is given with an angle to the x-axis rather than with a a rise and run type of format. So the first thing we're going to do is exactly as we just said. We're going to resolve all three forces into their x and y components, add the respective components together to get the resultant, and then find the magnitude and angle from those resultant horizontal and vertical components. All right, so let's start off with F1. Well, F1 is easy to write. It has 0 length in the horizontal direction, so we'll write 0I. And it has 300 newtons of magnitude, if you will, in the vertical direction. So that's 300J, and these are units of newtons. And then F2, you notice, is the one off to the left. So here we have to be a little bit careful and make sure that we're using sines and cosines appropriately, but we are measuring from the x-axis, so the horizontal component is going to be the cosine component, thinking of F2 as the hypotenuse of a right triangle. So we'll have negative 450 times the cosine of 45 to indicate that it's in the negative I direction. And then we've got plus 450 sine of 45 degrees, because F2, of course, has a positive magnitude in the J direction. And then the next thing to do is to punch the numbers into your calculator. When you do that, then you see the numbers we get, 318.2, one's positive, one's negative, of course. And now we have written both F1 and F2 in their horizontal and vertical components. Then F3, we can simply use the 3, 4, 5 triangle that is given there to scale the hypotenuse, which is a 600 Newton hypotenuse, along the various directions. So for example, the vertical component, the J component, is going to be 4/5 of 600. Okay, if you need to pause the video and think about that, you should. But if you're familiar with triangles, that should make some sense. So we're using the 3, 4, 5 geometry to scale the 600 Newton force for the J component there. And then for the X component, notice that the horizontal, the run of that triangle is 3, so 3/5 of 600 would be the horizontal length of F3. Or the horizontal magnitude, I should say, of F3. So now notice that F1, F2, and F3 are all resolved into I and J components. So the next thing we'll do is simply add all the I components together. So we've got F sub 1x plus F sub 2x plus F sub 3x there, times I, and then the same thing for the vertical components along the J direction. And after punching the numbers into a calculator, I suppose you could do it by hand, there is the resultant vector in Cartesian components. After that, we'll calculate the resultant magnitude by simply using Pythagorean's theorem, square root of the sum of the squares of the two components, 41.8 and 1,098. And then to find the angle, simply take the inverse tangent of the vertical component, which is the J component, 1,098, divided by the horizontal component, 41.8. And, there it is. It's 87.8 degrees. Now, what's wrong with the picture? Well, that doesn't look like 87.8 degrees to me. That looks like 45. So really, FR is almost oriented parallel to the y-axis. It's not quite at 90 degrees, but it's getting pretty close. So if we'd drawn that correctly, FR would be much more inclined and closer to the y-axis than it is. Here's another example. We've got a pipe with a force acting on it of 30 pounds, and that force acts at a 30-degree angle to a coordinate u, or a direction u. Now, there's a direction v, but direction v is not a vertical direction. It's 15 degrees off of vertical. So how will we resolve this force along the u and the v axes? Well, it's pretty straightforward. We will construct lines parallel to the u and v axis, or axes, sort of the reverse parallelogram, so resolving the 30-pound force with a parallelogram. And then find the magnitude of those components using the law of sines. So let's look through that solution and see how that works. So the first thing we do is we draw the line through the tip of the force, F, that is parallel to U. And then we draw another line through the tip of that force that is parallel to V. Now, of course, the length of F sub U, okay, there at the top, is going to be the amount of length that F provides on the u-axis. You can think about it this way. Think about a light shining down along the v direction, and the tip of F will fall on u right where you see there. And so the length of the shadow of the vector F is what we're really interested in. So it's F sub u. F sub v then is the magnitude of the force along axis v. Now, what exactly are those? Well, we could actually rearrange things. We could move f sub v over to the left so that it actually lies on the v-axis, and then extract that triangle and draw it off to the side. If you do that, you would realize that there's a 30-degree angle in the upper right corner of this triangle. It's because of the 30-degree angle of vector f with respect to u. There is a 105-degree angle between fv and fu, which makes sense because you notice it's more than 90. In fact, it's 15 degrees more than 90, which is 105. And then if you take 120, subtract 105, subtract 30, you'd find that you have a 45-degree angle then in the lower left corner. Another way to do that would be to realize that u is horizontal, the vertical line is 90 degrees from it. So if we simply take 90 degrees, subtract 15, subtract 30, we'll get 45. And that's the last angle in this triangle. So now all we're really doing is playing around with a triangle. And to calculate the magnitude of f sub u and f sub v, what we need to do is use the law of sines. So this is a more general triangle than a right triangle. And maybe you remember the law of sines, maybe you don't. It's a pretty easy one because all it says is that side A divided by the sine of the angle opposite that side, notice it's sine of little a, is equal to side B divided by the sine of the angle opposite that side, which is lowercase b, and so on and so forth for side C. So the law of sines, once you write the first one down, the other two are pretty easy. You just have to make sure you're dividing by sine and not write cosine. Then it's pretty easy. And it's easy to remember that it's the angle opposite. That, at least for me, that just kind of makes sense, I guess. I don't remember the derivation of the law, but it works for a general triangle. So what that means is that if we've got essentially a magnitude of 30 pounds on one side, we should be able to relate that side to the f sub u and the f sub v sides along with the angles that are opposite those sides. So here it is, 30 pounds over sine of 105, because the 105-degree angle is opposite the 30-pound side, is equal to f sub u divided by sine of the angle opposite it, which is 45 degrees, which is also equal to f sub v divided by sine of the angle opposite it, which is the 30-degree angle. And then all you've got to do is a little bit of algebra to rearrange things. Notice the first term, 30 pounds over sine of 105, is just a number. And all you'd have to do is multiply that by sine of 45 to get f sub u, or multiply by sine of 30 to get f sub v, and that's what's done next. So there's the magnitude of the force as it's resolved on the u and v axes. Now, you couldn't check your work by taking these two and adding them with the square root of the sum of the squares. As a matter of fact, what you'd have to do is use the law of cosines to figure out whether or not you got it right. Because, of course, these two should add up vectorially to 30 pounds. Now let's challenge the concept quiz. Can you resolve a two-dimensional vector along two directions which are not at 90 degrees to each other? Well, I certainly hope so. We just did. Was it a unique resolution? Actually, yes, it is. You might say, well, wait a second. You could have moved f sub v over to the right instead of moving it to the left. Yeah, that's true, but it's still the same magnitude. You see, an interesting thing about vectors is it doesn't really matter where they are. As long as they have a magnitude and direction, they're the same vector. You can put them out on Alpha Centauri if you want. As long as it has the same magnitude and direction, it's the same vector. So the answer is, of course, C. Yes, you can resolve them, and uniquely. What if you tried to resolve a 2D vector along three directions? So something like, they give an example here, 0 degrees, 60 degrees, and 120 degrees. Well, then you could, but it would not be unique because you could put different amounts of the vectors on these three axes and actually an infinite number of combinations. And so A would be the correct answer there. So now I would challenge you to go back and look at the quiz at the beginning and see what you can do. I also challenge you to go through the group problem solving. We would normally do this in class if we were in class. But go through this and see if you can come up with a solution for this. Let's see about the attention quiz. Resolve f along x and y axes and write it in vector form. Well, let's just look at f. It's 80 newtons, and it has obviously a horizontal, a positive horizontal component. It has a negative vertical component. So one of the problems that I encounter is that students often think that cosine always goes with the horizontal direction and sine always goes with the vertical direction. But that's not the case. That only works when you're measuring the angle relative to the horizontal axis. Notice that the 30-degree angle here is being measured relative to the vertical axis. So if you think about this as a right triangle, maybe you would draw a line coming down from the origin to be horizontal from the tip of vector f and then over to vector f. So let's imagine that triangle. Notice that the 30-degree angle is opposite of the horizontal length. So if we want the length along the x-axis, since 30 degrees is opposite that length, we will have to use sine. So I'm looking for anything, number one, that will have a positive x component. Well, they all do. All the I components are positive. But we'll have a negative j component, and that is only a and c. So we know b and d are wrong because we know this vector has a negative j component or a negative y-axis component. But should we use sine or cosine? That's really the only thing left. Well, for the horizontal component, we just mentioned that that horizontal component is opposite of the 30-degree angle. So to get the horizontal component, we'll have to use sine. Well, A uses cosine. That can't be right. So C is the only one that makes sense because they've used sine for the horizontal component, and then they use cosine for the vertical component. So the correct answer is C. Okay, 2. Determine the magnitude of the resultant F1 plus F2 force in newtons. So F1 is 10I plus 20J, and F2 is 20I plus 20J. Now they've set this up to make it easy. What do we need to do? Well, we need to add the components. So 10I plus 20I. Okay, that's the x component of F1 and F2. Well, that's easy. That's 30. And then we need to add the vertical components of F1 and F2. Well, both of those are 20. 20 plus 20 is 40. So then in order to calculate the magnitude of that resultant vector, basically what we have is a horizontal component and vertical component. We've got a right triangle. Take the square root of the sum of the squares. Use Pythagorean's theorem. So we need 30 squared plus 40 squared. And of course, if you do the math and then take the square root afterwards, you'll find that the result is 50 newtons. And so that is case C, because again, they've given us easy numbers, essentially a 3, 4, 5 triangle.